Okay, let's take a look at how to find the center of mass of some system or maybe some extended object. So I guess in general, let's start with the easiest case. Um, let's take an object right here and let's make it a mass of 4 kilograms. And then let's put another object, let's put another object 10 meters away, and we'll make that other object only 1 kilogram. Okay, so we can talk about where is the center of mass of this system. And so hopefully it makes sense that the center mass is probably going to be somewhere around this area here. It is going to be on a line connecting the two, and it's going to be closer to the 4 kilogram mass because the 4 kilogram mass is going to be a more important piece of information than the 1 kilogram mass. So you come up with some coordinate system, and I can prove to you that the coordinate system doesn't matter. So let's say we have this. And so what you want to think about is that the center mass, which we can call x bar, right, the average center mass, and we only need to look at x because in this case it's not a two-dimensional thing. So x center mass is what? Well, algebraically, and we can do this algebraically because we have a finite thing, it's each individual mass, m1 at its x1, m2 at x2, m3 at x3 plus dot 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 for as many different particles that we have, all divided by capital M, which is the total mass. Now think about what this is saying. This is just how we find the average of anything. We take each position and we weight it, meaning we multiply it by the mass that's at that location, and then we divide by the total mass. And that gives us the average center mass of the total system. Just think about if you multiplied this M over here, that would even make more sense. You know, the total mass at some average position is then the summation of all these individual masses multiplied by their positions. So if we follow this in this same format, we have 4 kilograms at a position of 0 plus 1 kilogram at a position of 10 divided by a total mass of 5 kilograms. Okay, so this is 4 times 0, so we have 0 plus 10 over 5, and we get 2, and the units there, of course, would be meters, and that's what we would expect. 2 meters from our origin, so the center mass of this system is located right there. And if you think about how that works, if this is 2 meters, then this distance is 8 meters, and since this is 4 times more massive than this one, then the center mass is actually 4 times closer to this one than that one. Those proportions have to make sense. You know, we're going to use center mass for a variety of things, but certainly we could talk about the center of mass being the balance point, right? So if you took a 4 kilogram sphere and you connected it to another 1 kilogram sphere, and you claimed that the rod itself didn't have any mass, so it was a negligible mass rod, then the balance point, right, so we want to put a fulcrum, we'd want to put the fulcrum on the center mass of that system, which we just proved was 2 meters away from that and 4 meters away from that. I want to prove to you that the system doesn't matter, or excuse me, the coordinate system, that choice didn't matter. So we'll take the same situation, 4 kilograms, 1 kilogram, 10 meters away, except now, let's say we thought this was our coordinate system. Okay, and I'll follow that same format. So we have 4 kilograms at a position of negative 10 plus 1 kilogram at a position of 0 divided by 5 total kilograms to give us our center mass, right? Same thing I did over here. Each mass multiplied by its position divided by the total mass. So this is negative 40 plus 0. Negative 40 over 8 is negative 8. And so then the center mass is at a position of negative 8. Well, where's negative 8 in this coordinate system? It's right here. And hopefully you can see that the center mass is still in the same spot, again, regardless of the coordinate system that I picked. Okay? Now, can you do two-dimensional things? Of course you can. You can do whatever you want. You can have as many objects as you want. You know, we could have a system where we have an object located here, an object located here, an object located here, and maybe even another object located here. Again, you can pick whatever reference point you want, and you can think about, well, where should the center of mass be? Well, let's make our coordinate system look something like this. And let's make them all the same weight. So they're all like 1 kilogram. And let's say they're all 1 meter apart from each other. Well, see how there are 3 kilograms here and only 1 kilogram up? So doesn't it make sense that vertically the center mass is actually fairly close to the 3, right? Not halfway here, not here, but somewhere in this range. And then horizontally, if you think of this being halfway, see how there's 2 over here and only 1 over here? So our x center mass is going to be somewhere. So I would predict somewhere like in that range is the center mass of that system. And all you have to do is do the same thing. You just have to do it in 2 dimensions. Okay, so let's do it for this one and say each one of these is 1 meter away. So that's a meter, and then that's another meter, and they're all just 1 kilogram. So we have 4 discrete objects. They're each 1 kilogram and they're each 1 meter away. And I'm predicting that this dot right here represents somewhere that the center mass is. All right, so let's do this. X center of mass. Okay, so this is my system. So this mass is at a position of 0. So 1 kilogram is at 0. This one is at a position of 0. Again, then we're talking horizontally. That one's at a position of 1, and that's at a position of 2. And I want to divide by the total mass, which is 4. So 0, 0, 1, 2, and I get 3/4. And again, 3/4. Maybe I should have put it a little more to the right. That might look like more like x is a half. So x is 3/4. So somewhere over here. If that's a half, then that's 3/4. So horizontally, we know that we're somewhere on that line. And then vertically, y center of mass is each one of them weighted on their vertical position. Well, this one's really easy, because this one is at a position of 1, and all of these other masses have a vertical position of 0. 0, 0, 0 as far as their y coordinate, and divide by the total, and then we get 1/4. Okay, and that vertically I did a better job, because that would be a half vertically, and that would be a quarter. So even though I guessed right here, the real center mass of the system is an x coordinate of 3/4 and a y coordinate of 1/4. So that dot right there is the center mass. And again, we can do it in 3 dimensions if we needed to, but it's the same thing. There's going to be an AP problem that's very similar to this, where they do something like a wire. And so they'll put a wire, maybe a wire like this. And where's the center mass? And so what you can do is, you can't just take this total wire and break it down, but you can break each piece down into a point particle. So see how right there, I'm going to say that wire is really all located there. That wire is really a point particle. So I can take each wire and look at its own center mass of the wire. I can call that 1 kilogram, that 2 kilograms, 2 kilograms, and 2 kilograms. Okay, let's say that the whole thing is 2 meters long, or actually let's just call it L long. Okay, let's say each one of these things is L long. So from there to there is some distance L. And so where do you expect the center of mass to be? Well, if you think about horizontally, there's more wire to the left than there is to the right. So then it's probably going to be something less than half of L. And then if you think vertically, there's more wire below than there is above, right? It's missing that piece above. So it's going to be a little less than half in both ways. So again, we could do this same thing for this object. And so we could say x center mass, and our coordinate system could be something like this. That's our coordinate system. So we have 2 at a position of 0. We have 2 that's at a position of L over 2. We have 1 that's a position of L over 4. And then this guy is at a position of L. Again, those are all its horizontal positions. And then I have a total of 7 kilograms. And then I just have some math here. Okay, so that's 0, 1, a quarter, and 2. Okay, so that's 2 plus 1 is 3, plus a quarter. So that's 3 1/4. 3¼ over 7. So that's 13 over 7, which is 13 over 28. And as we expected, our x center mass is slightly less than half, right? Because there's just a little more mass to the left. If you drew this down here, there's more mass to the left of this red and to the right of this red. So our x center mass is just to the left. And then we're going to do the same thing vertically. You can come over here and do that. So the y center mass of this guy, 2, is at a vertical position of L over 2. That guy's at a position, 1 kilogram is a position of L. This guy has a y vertical position of 0. And then that guy's at a position of L over 2. And then of course the total is still 7. And what do we get here? Okay, so this is 1, 1, and 1. That's easy. We actually just get 3/7 L. Oh, sorry. Sorry about that. This was 3¼ L, so this is 13/28 L, whatever L is. L is just the length, some pre-designed things. So now we know. So it's slightly less than half, 3/7 L, and then 13/28 L. So hopefully that kind of makes sense of how that worked, but we can do it for this. Now, all of these were discrete things, like a point is here, and a point is here, and a point is here. Well, the harder part is what happens if we have an object that's more of an extended object, and I just want to find the center mass of something. So let's look at a board first, and this first part's going to be kind of silly because it's going to be obvious that if you take a board and it's uniformly distributed, that the center mass is in fact in the center. But I just want to kind of go through this math here. Okay, so there's my board, and I'm going to put my origin here, and I'm going to say that this vertically is skinny enough that I don't have to worry about it. Clearly half is above and half is below the red line, so vertically. And then I know that the center mass is halfway, but I want to prove that. And I want to think about how that works. So I want to show you that calculus and algebra agree. So x center mass equals m1 x1 plus m2 x2 plus dot dot dot, all divided by m. And then the calculus version of the x center mass is what? The accumulation. That's what this is doing. It's accumulating all the little bitty masses, which we call dm, based on their particular x location, divided by capital M. These are the same formulas. This is the algebra discrete formula where you have a mass here and a mass here and a mass here. And then what happens if you have some one object? Well, if you want to find the center mass, you have to take that object, as we do in all calculus, and we're going to break it up in an infinite number of pieces. Each piece is going to have a mass equal to dm. Okay, and then what do we do with all those dm's? Dm is like each one of these m1s, m2, they're all the same, but they're all at a different location x. Well, you sum them up, and then you divide by that total, and that gives you the average position of each one of those pieces. Okay, so what is dm? Well, dm is the mass that's located right here. Well, the mass that's located right here also can be viewed as the density, which is lambda times the thickness. Again, think about what lambda is. It's a linear density. It's kilograms per meter. If you take the kilograms per meter of your wood and you multiply by the meters, again, dm is the mass of this guy, but the thickness of this guy, meaning the width, is actually dx. So if you take kilograms per meter times meters, then you get the kilograms of that particular object. Now, in this case, if it's a uniform dense thing, we can say dm is just the total mass divided by the total length times dx, right? That is how you'd find density if something is uniform. You just take the total mass divided by the total length. For example, let's say this whole thing was 10 kilograms, was its mass, and its length was 5 meters, then its lambda would be 2 kilograms per meter. Okay, now I'm going to stay in the abstract here, but if you wanted to, you could just put a 2 in for lambda, right? This quantity is just 2 for this particular thing. So what we have here is we're integrating lambda. Actually, I'll put in m over L times dx. That's dm times x all over m. Okay, look what happens here. M can get factored out of the integral, so can L. And then you're integrating x dx. And what are you going to integrate from? We're going to integrate across the whole board, so from 0 to L, and then divide by m. Hopefully it's clear that this m and this m cancel. So you're left with 1 over L times the integral of x, which is x squared over 2 from 0 to L, which is nice because you get L squared over 2 divided by L, and of course you get L over 2. And again, that was a very obvious result. Duh. Of course the center of mass of a board is in its center if the density of the board is uniform. Now the question becomes, well, where's the center of mass if it's not? Okay, what if, and now I'm going to go to the red, what if lambda was like kx? So we want to look at a situation where the board has non-uniform density. Okay, so you got to imagine what that would mean for our board here. So we're going to take our board, still has a total mass of m, still has a length of L, but somehow lambda, meaning the density of the board, kilograms per meter, is proportional to x. What that means, k is just some growth constant. It could be 2, it could be 5, whatever. And that means is, when we look at all these segments and we break it up, the density of each one of these pieces is getting bigger and bigger and bigger. So you looked at like this piece on the end, and let's just give an example. Let's say lambda in this case is equal to like 4x or something. Okay, that would mean that the density here, when x is equal to L, is like 4L, and the density here would be half as much, and the density here is almost nothing. So each one of these things have the same thickness, but they're different densities, so they have different masses, and so the center mass is not going to be in the center. It can't be in the center because this doesn't cancel with this anymore. If you look up here, if this is the exact same mass as this is, then the center mass of those two is in the center. These two balance in the center, these two balance in the center, but there's no balance here. And so we have to use calculus to figure that out. And so we do the exact same procedure. Nothing of what I said up here changes at all, except instead of lambda being some constant m over L, which is not a function of x, we just got to make lambda kx. And so we go into the same integral. It's the same integral right here or right here, same thing right here. The x center mass is the integral of dm, and dm is just the density, kx, times the thickness. Okay? That's still each mass. It's the density of each mass times the thickness of each mass gives the mass of each one of those parts times x, all divided by m. Again, see where there's an m over L, and now it's a kx. Lambda is some function of x. We can still factor the k and the m out. Okay, and now we end up integrating x squared dx from 0 to L, and we get k over m, x cubed over 3 from 0 to L, and we get k L cubed over 3m. Okay, that's the center mass. And so the center mass is a function of k, L, and m. And you're like, wait a second here. What is then m in terms of k and L? All right, so now we actually have to do a little bit more, because now we need to figure out, well, what is then this total mass? Well, the total mass clearly is the sum of all the individual masses, dm. Well, dm all by itself is exactly what we said right here. dm is kx times dx from 0 to L. Well, that's kx squared over 2 from 0 to L, which says then the total mass, which is clearly the sum of all the little bitty masses, is kl squared over 2. And now when you make the substitution, this is the total mass in terms of K and L. So we have KL cubed over 3 times the total mass, which is KL squared over 2. Look what happens here. This 2's in the denominator, so you get 2 thirds. The K's cancel. L cubed over L squared is L. And we just showed that the center of mass is at 2/3 L, and it's actually independent of K. K can be 4, K can be 5, K can be 6. As long as the density grows linearly, then the center mass will always be at 2/3 L. So somewhere like right here, meaning these count way more than these do, so the center mass shifted and actually shifted exactly to 2/3 L. Obviously this involves a decent amount of calculus and you're going to have to look this over, but the easy one was right at the beginning when it was a constant density, and of course we got L over 2. Then I changed the density to make the density some function of x. I did the same procedure, meaning the center mass is always this. I mean, this check mark, that's always the formula for the center mass. Just dm was a little more complicated. I got the center mass in terms of K and L, but I really wanted the center mass in terms of just L, so I need to get rid of the K. So then down here I did this extra step. I needed to figure out what the total mass was in terms of K. The total mass was the accumulation of all the little bitty masses. Each little bitty mass was still kx dx, just like it was here. I integrate all the little masses from 0 to L to get the total mass. This was the total mass. This was equal to capital M. I then substituted that value into capital M, simplified this algebraic expression, and then got the x center mass for a situation in which lambda, the linear mass density, grows with x. Okay?